What would happen if dark energy didn't exist? This question raises a fascinating range of possibilities that challenge our current understanding of the universe and the physical laws that govern it. Over the past 25 years, the observation that the expansion of the universe appears to be accelerating has led astronomers to one of the greatest cosmological discoveries: dark energy, a mysterious force that is believed to be driving the universe to expand at an increasingly faster rate. Although this is the most widely accepted explanation, new theoretical models are challenging this view, suggesting that there might be another way to explain the acceleration of expansion without relying on dark energy. One of these alternative models is the timescape model, developed by theoretical physicist David Wiltshire. According to this theory, the accelerated expansion is not due to an external force like dark energy, but rather to a phenomenon related to the way time flows and the uneven distribution of matter in the universe. Recently, two studies by Wiltshire's group have shown that this model can correctly explain some cosmological data without relying on dark energy. This raises an important question: does dark energy really exist? To answer this question, it is useful to explore the timescape model in more detail and compare it to the standard cosmological model, which incorporates dark energy. During the 20th century, the universe ceased to be considered a static and unchanging entity. In 1929, the great astronomer Edwin Hubble discovered that galaxies are moving away from us, and that the farther they are, the faster they move, leading to the formulation of the concept of the expanding universe. Initially, it was believed that this expansion would inevitably slow down under the influence of gravity. However, in the 1990s, two groups of astronomers observing Type Ia supernovae made a shocking discovery: the expansion of the universe was actually accelerating. This phenomenon earned the Nobel Prize in Physics in 2011, recognizing the revolutionary shift in our understanding of the cosmos. To explain this acceleration, cosmologists introduced the idea of dark energy, a gravitational force that would be responsible for the expansion of space at an increasing rate. In the standard cosmological model, dark energy makes up about 70% of the universe, yet its nature remains one of the greatest scientific mysteries. We cannot see it directly, it does not emit light, and we can only study it through its gravitational effects. One possible interpretation of dark energy is that it is a form of energy tied to empty space itself. However, a fundamental question must be asked: is this interpretation correct? There are alternative theories that could explain the acceleration of expansion without dark energy, for example, by modifying Einstein's general theory of relativity. Some proposals, however, attempt to keep general relativity intact without introducing new cosmic forces. In 2007, David Wiltshire introduced the timescape model, which falls into this second category. According to the timescape model, general relativity remains valid, but the apparent acceleration of expansion is not due to an external force. Rather, it is an illusion caused by the uneven distribution of matter and the flow of time in the universe. This concept may seem complex, so let's try to simplify it. A fundamental principle of the standard cosmological model is the cosmological principle, which states that, on large scales, the universe is homogeneous and isotropic, meaning that matter is uniformly distributed. However, we know that the universe is not perfectly homogeneous. There are very dense regions and empty ones, and matter is distributed in a cosmic web made up of galaxies and galaxy clusters. In the standard cosmological model, these irregularities are considered small perturbations on a uniform background, which can be ignored when calculating the overall expansion. In the timescape model, however, these irregularities are taken into account. According to general relativity, time flows more slowly in the presence of a strong gravitational field, a phenomenon known as gravitational time dilation, which has been observed and measured in many instances, such as when correcting errors in GPS satellites. So what happens if this effect is applied on a cosmological scale? In denser regions, time flows more slowly compared to less dense areas. In the timescape model, this factor is taken into account to avoid errors in calculating the universe's expansion. If an observer is in a high-density region, expansion will appear to be accelerating. In reality, this is a matter of perspective. Observers in different regions of the universe measure different expansion rates due to varying time dilation. Essentially, The timescape model suggests that there is no true acceleration of the universe, but rather that the disparity in time measurements across different regions creates the impression of accelerated expansion. The key aspect of this model is that it must make predictions that can be tested against observational data. In fact, the timescape model is able to make accurate predictions, such as the luminosity of type Ia supernovae, which have been used to measure cosmic distances. In the standard cosmological model, these supernovae appear dimmer, a phenomenon interpreted as a sign of accelerated expansion. However, in the timescape model, this same behavior can be explained without invoking dark energy. Recent studies conducted by Wiltshire's team, which analyzed over 1,500 type Ia supernovae, have shown that the timescape model's predictions fit real data. This has raised a new question. What if dark energy doesn't exist at all? However, it is important to note that the timescape model is still in development and cannot yet explain all aspects of the universe, while the standard cosmological model continues to provide explanations for a wide range of cosmological observations, such as fluctuations in the cosmic microwave background radiation, the distribution of matter, and gravitational lensing phenomena. While the timescape model offers an intriguing and alternative proposal, the standard cosmological model remains the most widely accepted theory. However, in the future, with the acquisition of new data, such as those expected from the European Space Agency's Euclid mission, new evidence may emerge that supports an alternative theory. Science, as always, is constantly evolving. If one day we discover that the standard cosmological model is less adequate, we will embrace a new model that better explains the data. For now, we can only wait and see which direction scientific discoveries take. Thank you for watching. Leave a like and subscribe to the channel so you don't miss future videos.